Let's begin with a feeling, not a number, not a unit. Just a feeling. You step outside on a winter night. Your breath becomes mist. Your fingers tighten. The silence settles around you like a blanket of stars. Cold. We know it. We fear it. Somehow we're drawn to it. But what is cold? Let's take a slow step back and try to understand it. Not just as discomfort, but as something much deeper. Something written into the very bones of the universe. Temperature isn't just how hot or how cold something is. It's actually a measure of motion, the movement of atoms and molecules. When something is warm, its particles are jiggling, spinning, vibrating, and when it's cold, those same particles move more slowly. Less chaos, less motion. The colder it gets, the more still everything becomes. So in a sense, cold is the quieting of matter, a soft slowing down of the dance of energy. Now imagine taking that stillness further and further until everything stops. No motion, no vibration, just absolute stillness. That, in theory, would be absolute zero. Absolute zero is 0 Kelvin. That's about negative 273.15 degrees Celsius. At this point, atoms reach their lowest possible energy state. No more movement, no more vibration. It's the coldest anything can ever be. But here's the twist. You can't actually reach it. Not fully. No matter how advanced our technology gets, the laws of quantum mechanics say there will always be a tiny flicker of energy left. This is called zero-point energy, a kind of built-in hum of the universe that can never fully be silenced. So while we can approach absolute zero, we can never quite touch it. The coldest places in the universe, the coldest labs on Earth, they get close, but never perfectly still. There's always a whisper. Why does this matter? Because cold isn't just about temperature, it's a lens, a perspective on motion, energy, time, and even life. In the language of physics, cold means order, stillness, simplicity. It's not chaos, it's the quiet end of a long process of losing energy. And in that quiet, strange things happen. Atoms behave like waves, matter blurs and overlaps, quantum rules begin to dominate. To study cold is to study what happens when the universe slows down. And that gives us a unique glimpse, not just into physical processes, but into the future. Because if heat is energy, and energy is the engine of change, then cold is what waits when the engine winds down. So as we begin this journey into the darkest, coldest corners of the cosmos, let's remember, cold is not emptiness, it is not death, it is not failure. Cold is peace, cold is quiet, cold is the absence of hurry, and it tells us something profound. Even the universe rests, even the stars grow silent, and in that silence we find something sacred. Stillness. Let's leave Earth behind. No sound, no breeze, no footsteps, just you and the stars. You're drifting quietly through space. Vast, endless, dark, and cold. But just how cold is space? Many people imagine it as the coldest place possible. A perfect vacuum, completely frozen. But the truth is a little more complicated, and a lot more beautiful. Despite how it feels, the universe isn't entirely cold. Even in the deepest, most empty regions of intergalactic space, there is a quiet warmth. A kind of background temperature that wraps the cosmos like a faded memory. This soft glow is called the cosmic microwave background, and it tells the story of the early universe. Roughly 13.8 billion years ago, the universe was hot. Unimaginably hot. Everything compressed into a dense, glowing soup of particles and light. Then it expanded, it cooled, and eventually light was able to move freely through space. That ancient light, the oldest in the universe, is still traveling. Still warming space. Just a little. It's been stretched out by the expansion of space itself, fading into microwave radiation, whispers of what once was. And today, the temperature of that background glow is about 2.7 Kelvin. That's just above absolute zero. Colder than liquid nitrogen. Colder than the darkest Antarctic night. But still, not the coldest. You see, space isn't truly empty. There are atoms floating in the void. Particles left over from stars, from galaxies, from ancient cosmic events. Faint radiation, ghost-like neutrinos, even gravity waves. All of it adds up to just a little bit of warmth. So even in the quietest corners of space, temperature exists. Just barely. But it's cold enough to slow everything down. And in that slowness, something special happens. Between the stars, between galaxies, there are pockets of gas, thin, fragile, almost invisible. These are called molecular clouds, and in them new stars are born. Ironically, life begins in cold places. Gravity slowly pulls matter together, and from the cold, warmth emerges. Still, there are colder places than even this. Colder than the interstellar clouds. Colder than the faint whisper of the microwave background. Rare places, strange places, where physics stretches to its quietest extremes. And one of those places is colder than the universe itself. In the next part of our journey, we'll visit the coldest natural object ever found in space. A place so cold, so quiet, it defies the background warmth of the cosmos. The Boomerang Nebula. Imagine floating into a region of space so cold, it's colder than the universe itself. That sounds impossible. After all, the cosmic microwave background, that gentle afterglow of the Big Bang, sets the baseline for temperature in the universe. 2.7 Kelvin. Just above absolute zero. That should be the limit. The cosmic floor. And yet, we found something colder. It's called the Boomerang Nebula. Roughly 5,000 light-years away in the constellation Centaurus, it doesn't look particularly strange at first. Just a faint blur of gas expanding into space. But when astronomers looked closer, they saw something breathtaking. The gas in this nebula is cooling at an incredible rate. So fast, so violently, that its temperature has dropped to just 1 Kelvin. Colder than the background radiation. Colder than deep space. Colder than anything else we've ever found in nature. Why? The answer lies in the way it's dying. The Boomerang Nebula is what we call a pre-planetary nebula. A dying star, much like our own sun will one day be, is shedding its outer layers. But it's not doing it slowly. It's blasting material into space at speeds of nearly 500,000 kilometers per hour. And that incredibly fast expansion causes the gas to cool. Fast movement leads to low pressure. Low pressure causes rapid cooling. And when that happens in the near vacuum of space, you get something extraordinary. A place colder than space itself. Now think about that for a moment. The death of a star, creating not fire but cold, not heat but stillness. A kind of frozen breath, expanding outward from something once so bright. In the Boomerang Nebula, the star's outer layers are cooling as they race away from the core. The gas isn't heated by collisions or radiation. It simply thins and chills. It's not eternal. Eventually, the nebula will warm back up. It will be lit by the inner core of the dying star, a white dwarf that will begin to glow as it collapses inward. But for now, for just this chapter of cosmic time, the Boomerang Nebula holds the title, the coldest known place in the natural universe. And here's the poetic twist. It's beautiful. If you could see it clearly, you'd witness arcs of delicate gas, stretching like icy wings, gently illuminated in soft, ghostly light. A moment in time. A pause in the warmth. A whisper of the end. And even colder places exist, but only in laboratories. Here on Earth, scientists have reached temperatures within billionths of a degree above absolute zero. They use lasers, magnetic fields, and ultra-high vacuum chambers to cool atoms until they begin to behave strangely. At those temperatures, atoms form something called a Bose-Einstein condensate. A new state of matter where particles lose their individual identity and behave as one, like a single wave, frozen in place. These man-made cold spots are fleeting, tiny, and carefully isolated from the rest of the world. But they tell us something profound. When you slow the universe down, when motion fades, when energy thins, the world becomes strange. The rules begin to blur. The classical becomes quantum. The solid becomes wave. Cold isn't just a temperature, it's a doorway into different physics, into different ways of being, and maybe into different ways of understanding what time, energy, and stillness really are. Next, we'll look beyond single stars and atoms. We'll step back, way back, and ask, what happens when the entire universe begins to cool? What lies at the end of cosmic time? Now, let's step back, far beyond the Boomerang Nebula, beyond the galaxies, beyond the last wandering stars, and let's imagine the future. Not tomorrow, not next year, but the deep, deep future. Trillions of years from now. What does the universe look like? When everything has cooled? What happens when the stars go out, the light fades, and time itself slows down? It's a strange thing to consider because when we think about endings, we often imagine noise, collapse, fire. But the end of the universe may be quiet, it may be cold. We're in what scientists call the stelliferous era, the age of stars. Galaxies are alive, stars are being born, planets circle suns, light fills the sky. But this won't last forever. Eventually, stars will run out of fuel. Some will explode. Others will shrink and fade. The bright cosmos will dim. We'll enter what's known as the degenerate era, a time when white dwarfs, neutron stars, and black holes remain. No more fusion. No more new light. Just the remains, glowing faintly. Even those remnants will fade. White dwarfs will cool into black dwarfs. Neutron stars will go quiet. Black holes will slowly evaporate through Hawking radiation. And then stillness, darkness, a universe stretched thin, cold, quiet, empty of structure. This is what physicists call the heat death of the universe. Ironically, it's not a fiery end, but the final consequence of heat spreading too far, of entropy reaching its maximum. Everything has equal energy. There's no more difference, no more potential, no more change. And if change is what time needs to exist, then time itself may come to a kind of end. Not because the clock stopped ticking, but because there's nothing left to tick toward. The universe rests. It's hard to imagine. A place where nothing happens, no light, no sound, no memory, no future. Just a thin scattering of particles adrift in an ocean of cold. But maybe there's a kind of peace in that. A final sigh, a cosmic exhale, a return to silence. The journey from heat to cold is not a failure, it's a process. The natural arc of energy finding balance, of chaos becoming stillness. And that same arc exists in everything, in stars, in lives, in thought, in time. Even now, as you listen, you're part of that unfolding. You are a warm consciousness floating in the brief springtime of the universe, before the quiet settles in again. And maybe that's what makes this moment so precious, that the universe for a little while can think, can wonder, can feel the cold and ask what it means. Thank you for listening. Let the stillness stay with you. Let the cold teach you not just of endings, but of beauty, of peace, of rest. Stay curious, stay warm, and always stay cosmic.